Hello, and welcome to the AI Research Roundup. I'm Alex, and today is May 8th, 2025. We're diving into an ICLR conference paper, miniCTX, Neural Theorem Proving with Long Contexts, published just over 3 months ago. This paper highlights that real-world theorem proving, often using interactive theorem provers like Lean, which are tools to help formalize proofs, needs lots of context. Current AI, or neural theorem provers, often don't use new context well. So this paper introduces miniCTX, a new benchmark, a standard test, to see how these AIs handle fresh, unseen contextual information from actual projects, employing a temporal split where test data is newer to avoid data contamination. Alright, so this table really lays out why miniCTX is a step forward. It compares different benchmarks, these standard tests for AI provers, across several key features. We see columns for the language used, whether they include premises, which are the starting assumptions for a proof, and if they use full context, meaning all the surrounding information from the original file. Notice how miniCTX is the only one here that ticks all the boxes, especially for providing that full context and using the temporal split we discussed, making it a more realistic test. And this figure really drives that point home, visually contrasting two approaches to testing these AI provers. On the left, you've got traditional large language model proving, where models train on existing theorems, often from large libraries like MathLib, which is a vast collection of formalized mathematics, and then test on standalone problems. But on the right, it depicts context-dependent proving. Here, the AI encounters theorems that depend on new formalizations, new definitions and lemmas, which are like smaller helper proofs, all within the same project. This highlights the importance of testing with this kind of rich, immediate context. Okay, so looking at this table 2, we get a clearer picture of the problem statistics for miniF2F compared to the new miniCTX benchmark. What really stands out is the context size, measured in tokens, which are essentially small pieces of text or code for the AI. miniCTX involves context sizes in the tens of thousands of tokens, vastly more than miniF2F. It also details things like in-file premises. These are assumptions or proven statements found within the same source file, and repo premises, which are similar assumptions but from other files in the same project. This data really underscores how miniCTX is designed to test the handling of extensive and varied contextual information. So to ensure this test of handling new information remains robust, Figure 2 shows how miniCTX is designed to stay ahead. We see a timeline. 2023-2024 into the future. Previous benchmarks used Lean theorems. These are formal statements to be proven, available before a certain point. But large language models have training cutoffs, meaning the date up to which their training data extends. This figure shows miniCTX is compiled with new Lean theorems, those appearing after these cutoffs, and it's planned to be regularly updated. This continuous updating is key to fairly testing, if models can truly reason with novel context. Alright, so building on how miniCTX tests the use of fresh information, Figure 3 here really clarifies two different training strategies. On one side, we see, quote, state tactic tuning. This method trains the AI to pick the next tactic, which is a command to advance the proof, based only on the current proof state or the immediate status of the mathematical argument in Lean. But then, on the other side, there's file tuning. This approach gives the AI much more to work with, including the surrounding file context, like new definitions, lemmas, which are smaller helper proofs, and the proof built up so far, in addition to that proof state. Okay, so this next table really quantifies the impact of these different approaches. It compares various methods, including that file tuning and state tactic tuning we just talked about, across two different test setups, or benchmarks. We also see some methods here with plus premise. This refers to providing the AI with selected prior statements, or premises, that might be helpful for the proof. Now, looking at the miniCTX test benchmark, where context is vital, file tuning achieves an average proof success rate of nearly 36%. That's a big leap from state tactic tuning at about 19.5%. really showing how crucial that file context is. So, wrapping up, these results really drive home a couple of key points. First, for AI to get good at mathematical reasoning, especially in complex systems like Lean, understanding the surrounding context, all those definitions and previous proofs, is absolutely critical. And second, this new benchmark, miniCTX, provides a much more realistic way to test and develop AI that can actually use this novel information effectively, with file tuning showing real promise. It's clear there's a lot of exciting work ahead in this area. Thanks for tuning in to the AI Research Roundup. I'm Alex, and I'll see you next time.